chemistry. So let's dig in. So for this discussion, we will be talking about your atomic absorption spectrophotometry and the different components, the basic components with regards to your AAS. So before we talk about your spectrophotometry, and if you haven't watched the video or the discussion regarding spectrophotometry, I will be giving you the link on the description box, and also somewhere here in your screen it will just pop out. So let's dig in. So for first and foremost, what is atomic absorption spectrophotometry? So your AAS is actually used to measure concentration by detecting the absorption of electromagnetic radiation by atoms rather than molecules. Yes, what you heard was right. What we are talking about now is no longer molecules. That is very much the respect and the job of your spectrophotometry. Now what we are measuring is the absorption of your atoms. So we are talking about atoms. So now I just want you to differentiate those two, because AAS and your spectrophotometry are two different instrumentation. So talking about your atoms, since we are talking about atoms, so the usual things that we measure using your AAS are these elements. Usually it's your aluminum, your calcium, your copper, your lead, your magnesium, your lithium, and your zinc. As you can see, most of these things are actually part of your electrolyte. Are your trace elements, and some are actually your heavy metals or your toxic elements that are usually seen in your patients. So some you can see them normally in a patient, and some you can see them if there is a lead poisoning or plumbism. Okay, so talking now about your atomic absorption spectrophotometry, your AAS is actually 100 times more sensitive than your FES. And if you're asking what is FES, that is flame emission spectrometry. So FES is somehow a very insensitive and non-specific method. That's why we are actually using AAS more than your FES. So AAS, your atomic absorption spectrophotometry, again, is 100 times more sensitive than your FES. So talking about the absorption of your atoms, maybe you're asking, how can we now determine the concentration of a particular atom, the concentration of a particular analyte or element using your AAS? So the amount of light absorbed is actually directly proportional to the concentration of your analyte. Okay, so it's very important for us to realize that, very much similar to your spectrophotometry, it's also directly proportional to the concentration. Okay, so how does your atomic absorption spectrophotometry works? Okay, so here's the thing. What we have are actually atoms on their ground state. So usually what we can actually collect from our patient are actually samples or analytes, and eventually those are only on its ground state. Okay, so they are on its ground state or in their neutral state. So what will happen is that they will now be excited. Okay, they will now be undergoing excitation, whereby they will be at their excited state. And then, as you all know, when you are when you are on an excited state, you will be shifting back to your ground state. Okay, and that what's happened to your atoms as well. They will be returning from excited state to their ground state, and in that process, they will now be emitting light. Okay, they will now be emitting light. So at the moment that your excited atom is returning back to its ground state, the process is actually through emitting a particular light. Okay? Through emitting a particular light. So again, your excited atoms, when they return to their ground state, they will start emitting light of the same energy as it absorbed. So the amount of energy, the type of energy, the wavelength of energy that your atom absorb will be the same amount of light when it comes to wavelength and energy that it will be emitting. So I hope that's clear. So I just want to go back again and explain that when we are doing atomic absorption spectrophotometry, what we have are atoms on its ground state. So for us to be able to measure them, we will be exposing them to a particular energy for them to be excited. And from excited, they will actually be returning to their ground state. Okay, they will be returning to their ground state, and in that process they will now be emitting light from that atom. Okay, so I hope that is clear. So this is actually the normal the simplest format or representation of the atomic absorption spectrophotometry instrumentation. What we have here are actually your light source. We also have your chopper. You also have your nebulizer, your atomizer, all on the same all on the same side, and then you have your monochromator, you have your photo detector, and then you also have your readout device. So let's go on one by one. The first one is of course your light source. So what does your light source do? So your light source first and foremost is of course the source of your incident light. So in AAS, we actually have two types of light source. The first one is actually your electrodeless discharge lamp and your halo cathode lamp. Okay, so let me first explain what is your electrodeless discharge lamp and your halo cathode lamp. So your electrodeless discharge lamp is consists of a bulb containing or filled with your argon and the element to be tested. So it actually uses radio frequency generator to excite the element. On the other hand, we also have your halo cathode lamp. What does your halo cathode lamp do? So it actually is consists of an evacuated gas tight chamber containing an anode, a cylindrical cathode, and an inert gas, usually argon as well, and your helium. So it actually is separated. It actually requires a separate lamp for each metal. Okay, so if you're measuring a particular element, like for example, it's your aluminum, a different lump is required for aluminum, a different lump is required for your copper, zinc, so on and so forth. And maybe you're asking, how does your halo cathode lump produces light? How does your electrodeless discharge lamp produces light? I hope you are actually have do you actually have your bishop with you on your side. So your halo cathode lamp, let me go first to your halo cathode lamp. So your halo cathode lamp produces light this way. So remember that within the chamber you have your helium and your argon. Okay? Now, we also have your cathode and your anode. So what will happen inside the gas tight chamber is that this helium and argon will now be attracted, the ions will be attracted to the cathode. So the moment that they are being attracted to the cathode, they will now be bumping into metals within the gas tight chamber. And if that happens, the bumping of those ions into those metal will cause its excitation. Okay? And again, when an ion is excited, as it returns back to its ground state, it will now be releasing your light. And that is how your halo cathode lamp produces light. It actually attracts first the ion to the cathode, bumping into the metals, and then eventually those ions are excited, and eventually they will be returning to its ground state, producing the light. Okay? On the other hand, we also have your electrodeless discharge lamp. The manner is actually very much similar to your halo cathode lamp. The only difference between the two is that it doesn't have your cathode or your anode in your electrodes discharge lamp. What we have are actually your radio frequency generator. So very much similar to your halo cathode lamp, we also have your ions in the form of your argon. So your argon are being excited how? Through your radio frequency generator. So the moment that again your argon is excited, it will return back to its ground state, now emitting your light. So that is how your AAS light source produces your light. Again, we have two types, your electrodeless discharge lamp and your halo cathode lamp. I hope my explanation was clear. So let's move on to the next part. which is your beam chopper. As you can see, your beam chopper is one unique feature of your atomic absorption spectrophotometry. And I want you to take note of this one very much. Um, I want you to take note of this because this is very much important. Okay, so your beam chopper, what does it do? It actually modulates the hollow cathode light beam. So isn't it that a light actually, when a light is being when your lighter is producing light, it's actually producing a light that is consistent when it comes to its intensity. So what does your beam chopper does? It actually produces pulses of light like what you are seeing in the GIF that I provided below. So in this case, the beam chopper now will cause the system to have pulses of light. Okay, pulses of light. And I just want you to hold on when it comes to the beam chopper, because as we go along, I will be explaining to you what is the importance of your beam chopper. So that is what your beam chopper does. Again, it modulates the hollow cathode light beam, and it actually produces pulses of light. So like a Christmas light, like this one, and also this one. So later on, I'll be explaining why is it very much important. So after your beam chopper, we go now to your nebulizer. Okay, we go now to your nebulizer. And this is again very important because again, going back to the definition of AAS, we are no longer measuring molecules but atoms. So how do we do that? That is through the help of your nebulizer, and later on by your flame or your atomizer. So let's move on to your nebulizer. Your nebulizer, its main goal is actually to deliver a fine spray of the sample containing your metallic ion into your flame or your cylinder, or in a nutshell, we can call it your atomizer. Okay, we can simply call this one your we can simply we can simply call that your atomizer. So when it comes to your nebulizer, it actually delivers your sample into your flame or your cylinder. So maybe you're asking, why do we have a flame and why do we have a cylinder? Okay, why do you have a flame and why do you have a cylinder? So here comes now your atomizer. So as you can see, you cannot see a cuvette or a sample cell here. Why? Simply because your flame or your burner or your graphite furnace is the sample cell of the instrument itself. Okay? So we deliver from the nebulizer, we deliver the sample going to your flame or going to your cylinder, which is in turn your atomizer, and at the very same time it is also the sample cell. When I say sample cell, it's the one that holds the sample while it is being measured. So what does your atomizer does? By the way, so your atomizer dissociates the solution into its neutral and individual atoms. So take for example, you have your sodium, your we have your elements that is bound to different molecules at the same time. We have your atoms that are bound either to a protein, to whatever molecule, biomolecule on your solution. Your atomizer's job is actually to produce an individual and a neutral atom out of that. And how do you do that? That is through your atomizer. And we actually have two types of atomizer. We have your flame atomizer and we have your electrothermal atomizer, which is your graphite furnace. In your electrothermal atomizer, you can actually hear it as well as the flameless atomic absorption spectrophotometry, because it doesn't use your flame anymore but it uses your graphite furnace. So let me explain to you what happened first. So as I was mentioning a while back, your atomizer is also your sample cell. This is where your sample is being held while it is being measured in the system. So your atomizer, let's go first to your flame atomizer, can actually be of propane in nature. Okay? Your flame atomizer can actually be a fuel gas. It can actually be of propane in nature, or acetylene with an oxidizing agent or a compressed gas, which is burned to produce a flame. So that is how your flame atomizer is. Okay? So again, coming from your nebulizer, you spray your sample into your flame atomizer for it to be atomized, and at the same time for it to be held while it is being measured. We also have your electrothermal atomizer, and this is again in your flameless atomic absorption. So we are using your graphite furnace. So what we have here are actually graphite cylinder. So from your nebulizer, your sample will be held in your graphite cylinder, and eventually that graphite cylinder will be subjected to increasing temperature, whereby your sample now will start to evaporize, and as your sample start to evaporize, it will now start to be liberated from whatever molecule it is bound, now forming an atomized sample. Okay, an atomized sample. So that's what happened between your flame atomizer and your electrothermal atomizer. So the only difference that in your flame atomizer there is flame, in your electrothermal atomizer there is no flame because you are using your graphite furnace. Again, your graphite cylinder holds your sample, and then your temperature will be increased, thereby evaporating the sample, forming now your atoms. Okay? So I hope we are clear. So that is for your atomizer. So again, going back, we did discuss your light source, we did discuss your beam chopper, your nebulizer, your flame or your atomizer in general. Now we go to your monochromator and your photodetector. We're actually nearing the end. So your monochromator, similarly to our spectrophotometer, is the actually controls the light absorbed by the sample. So the light absorbed by the sample is in pulses. Thus, the light it emits is also in pulses. So the monochromator isolate the desired emission line from the other lamp emission lines. So it also has your entrance and exit slit. So your monochromator in a nutshell um, isolate a particular light coming from your sample that it will now be delivering to your photodetector. Again, the photodetector we are using is your photomultiplier tube, the most sensitive. Why? Here comes now the explanation. We are using your photomultiplier tube because what we are measuring here in your AAS are actually bursts or pulses of light. I want us to return to bullet number 1 of your monochromator. Again, the light absorbed by the sample are in pulses. How does it happen? Okay, how does it happen? The light coming from your light source, again, is being chopped by your beam chopper, producing now only pulses of light. Okay? Pulses of light. And that pulses of light are being absorbed by the sample in that very same manner. Okay? So, your atoms are actually absorbing light by pulses and will also be emitting light by pulses. So imagine that it is actually blinking or twinkling, similar to your Christmas light. So the light that it receive are in pulses. So the light that will also be emitting is also in the form of pulses. Okay? Sir, madam, maybe you are wondering why is the pulses so important? I want you to remember this. In your atomic absorption spectrophotometry, there are two types of light, and that is the light coming from your light source, whether it is an electrodeless or a hollow cathode lamp. And of course, when you are using your flame atomizer, there is also light coming from your flame, correct? So those are two types of light. So the question now is that how can we discriminate the light coming from your light source and the one that is just coming from my flame? Okay? And what you want to measure is actually the light that is coming from your atoms that came from your light source. So how do you do that? What they did is actually to incorporate now your beam chopper. So that is what the beam chopper does. The beam chopper produces pulses of light. Therefore, your atoms also absorb pulses of light. Ergo, thus, it also be emitting pulses of light. And those pulses of light will the only light to be detected by your monochromator and your photo detector. And then the light coming from your flame will be electronically eliminated from the system. So imagine that, okay? Imagine that. I want you to imagine that as we are actually going through, okay, so take for example this one, your samples are in this part. As you can see from the light source, it's a continuous light, but after passing through the chopper, it will now be in pulses represented by the broken light. I hope you are following my laser. So my laser pointer. So it will now be in pulses. So the atoms, your analyte within that, will also be absorbing the light by pulses. Okay? It will now be absorbing the light by pulses. So what we want is to again, what do we want is to discriminate the light coming from the sample and the light coming from your flame. So how do we do that? Okay? The monochromator and your photo detector, your photomultiplier tube are programmed only to detect and only to measure the pulsating light or the pulses coming from your atoms. So in that case, the light coming from your flame or your burner will be electronically eliminated from the system. So in that case, you only will be able to measure the pulses of light. Therefore, you will now be correctly measuring the concentration of your molecule. Okay? So that's what your monochromator does there. So in your photodetector, again, it's your photomultiplier tube. Okay? One very good reason why the photomultiplier tube is that when you go back to the definition of photomultiplier tube, it is actually very much sensitive because it can detect quick bursts of light and short or low intensity light. And it is very important in the case of your atomic absorption spectrophotometry because, again, you are measuring pulses of light. So, in a nutshell, in simpler terms, your photomultiplier can detect quick bursts of light or quick pulses of light now coming from your sample or coming from your atoms. That's why when it comes to photodetector in your AAS, we only talk about one, and that is your photo multiplier tube. Okay? So, in a nutshell now, that is your atomic absorption spectrophotometry. You have your atomic absorption spectrophotometry already. You have your basic components, and of course, that is all about your atomic absorption spectrophotometry. We discussed the atomic absorption, the components, and of course the different function of those components within your atomic absorption spectrophotometry. So I hope you did learn something new today, and I hope I made myself clear. So one thing that I really need you to understand here are the pulses of light. Okay? The pulses of light because that's very important. So again, your atomic absorption spectrophotometry measures the light absorbed by your atoms. Okay? The light absorbed by your atoms. So to end this discussion, let me leave you this quote from Martin Luther King Jr. saying